weekly interactive and review for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carrizales, and Albert Isasi. The session will be recorded so that you may come back to it later if you need, or so others who may have missed on today's events will be able to come and watch it. Today, Math 1314 will be covering standard form of quadratic equation and graphing, and 1324 will be covering writing exponential equations into logarithm form. This event will be providing the Tejano passport points. This code will be posted at the end of the chat at the end of the session for the Tejano passport points. Thank you all. So now at this time, please mute your mics for the best sound experience. Otherwise, the feedback could interfere with the information we'll be sharing today. Without further ado, here is your presenter, Ms. Yvette Chuca.
Hello, everyone. Welcome to Friday Happy Math Hour. We are going to start with chapter 2. And so let's get started. So hopefully everybody that took the test already for chapter 1, hopefully your scores were what you were hoping. If you're taking your test this coming week, then good luck to you on that as well. We're going to go ahead and get started with chapter 2. And so one of the first things that we want to do is we're going to be looking at quadratic functions. And if you notice for quadratic functions, we know it's quadratic if the highest exponent is a 2. In chapter 1, we also saw functions that had a power of 3 and so on. So we're also going to be looking at those functions with higher or exponents. But for now, we'll look at the quadratic function. So a quadratic function has this form here. F of x is equal to ax squared plus bx plus c. And we also saw in chapter 1 that the graph of the quadratic function is a parabola, which we call a U-shape. And then we also saw that the parent function is x squared. And so what we're going to do is we're going to go ahead and look at the graph a little bit more in detail. And so this equation here is a general form, but we also have something called the standard form. And they both represent quadratic functions. They just have different ways of writing it. And so the first graph here, f of x is equal to x squared. Here we know that the parabola opens upward. And then the second one, f of x equals negative x squared. The negative is going to open downward. And so let's look at some other features. So again, here we know that it's going to open upward if the number in front of x is positive, and it's going to open downward if the number in front of x is negative. And the bottom part of this parabola here, we call this the vertex, and we also say it has a minimum point at 0, 0. And so the vertex can be found in two ways. One, we can use this formula here, or we can use the standard form. Now, if the parabola is opening downward, then the vertex is now going to have a maximum point. And so very closely here, we look at the standard form. The vertex can be found by taking our h in here and then the k. But if it's in the general form, then you'll have an option to write it as a standard form, or you can use this information here. Another feature that these parabolas have is the axis of symmetry, which is represented with this dotted green line. And the axis of symmetry is always going to be x equals to the x coordinate of the vertex. And so that's why we write it as x equals negative b over 2a. Or if it's in standard form, we write it as x equals h. And so what we want to do is take this general form and rewrite it in the standard form, and it's going to help us to identify the vertex, but it also helps us to be able to solve for the x-intercepts maybe a little bit quicker. And we also are familiar with the graphs, right? So in chapter 1, we saw the transformations. We know that the minus h causes the graph to move to the right, and the k causes the graph to move up since it's positive. And so our main interest here is getting this vertex. And so I'm going to walk you through the steps. But first, let's get familiar with finding the vertex. So if our equation looks like this, then what I like to do is I like to write the standard form. That way I can remember what I'm looking for here. So again, the vertex is h, and then we have k. And so in our situation here, our vertex is going to be -1 and 12. So it's the opposite of what we see in the parentheses. And if you think about the graph, if we were to graph this, the graph got shifted to the left 1 unit, causing us to be at the location of x equals -1. And then the 12 is going to keep the sign. Okay, so how do we complete the square? So I believe we have about 3 examples maybe so that we can see the steps. But what you want to do first is you want to group the x terms together. And so the x terms here are 4x squared and 8x. And then we're going to factor out any coefficient from the x squared. So we want x squared to have a 1. We don't want it to have anything else, just a 1. So the first step here, I'm going to regroup these together. So I'm going to put parentheses around the terms that have x's in them. And then I'm going to factor out this 4. So if I factor out the 4, then we get x squared. And really what we're doing is we're dividing 4 divided by 4 is 1. And 8 divided by 4 is going to be 2. So if we simplify, we end up with x squared and 2x. So you can always double check. So 4 times x squared is 4x squared. 4 times 2x is 8x. And so then our next step, now that we have a 1 in front of the x squared, is we're going to take half of b. So the number b is always going to be the number in front of x if it's written in general form. And so we're going to take half of that number. So half of that number is going to be 1. And then the next step is we're going to square it. So we're going to take half of it and then we're going to square it. So 1 squared is equal to 1. Your result, we want to add and subtract it into the parentheses. And when we do this, we're essentially just adding 0. So we're not changing the problem, we're just making it look a little bit different, but we're adding 0 here. So plus 1 and minus 1. Now the next step sounds a little silly because we just put these numbers in here, but now we're going to take out that negative. So this -1, we're going to bring it outside of the parentheses. However, if there's a number in front of the parentheses, we're going to multiply it. So 4 times -1 is equal to -4. So this -4, we're going to add it to the outside of the parentheses. So in this case, we have 16 minus 4, which is going to be 12. And if you notice in the parentheses, we leave this number here. So the reason we want to leave this number here is so that now if we look at this part of the polynomial, it's going to be able to factor. Yep. So if we look at this, we can factor the parentheses as x plus 1 and x plus 1. And since they're the same, we can write it as x plus 1 squared, and then we have plus 12. So now it's in standard form. So we can take the vertex from here. So the vertex will now be -1 and positive 12. Okay. So those were all the steps. We're going to do a few more. That way we can practice with it. But before we do that, I want to just highlight something here really quick because it's going to be helpful when we start looking at other things. So whenever you take half of b, we got 1. And so this number that you get here, that's what's going to be in your factors over here. So like x plus 1 and x plus 1. And you'll see that as we're doing the next examples. Okay, so let's look at another example. So here we have x squared plus 2x plus 1. So the first thing you want to do is we want to group these x terms together. So I have x squared plus 2x. You want to ask yourself, does x squared have a 1? Yes. So there's nothing that we need to factor out. Okay. So the next step is we're going to take half of 2. And so half of 2 is 1. And then we're going to square it. So 1 squared is also 1. So similar to the first one. Now we're going to add and subtract that 1, and then we have 1 and -1. And we want to bring this -1 outside of the parentheses. So now we end up with x squared plus 2x plus 1. If I bring the -1 outside, there's nothing for me to multiply it with. And so I'm just left with the -1. Okay, so 1 plus -1 is 0. And then the x squared plus the 2x plus 1 will factor as x plus 1 and x plus 1. And so we're left with f of x is equal to x plus 1 squared. So to find the vertex would be -1, but then there's no constant here, so that's going to be 0. Okay, so again, so our vertex is -1 and 0. The axis of symmetry, as I mentioned earlier, it's always going to be this x coordinate, so we say x is equal to -1. Okay, so let's look at this one that has a number 2 here. So here we're going to go ahead and regroup the x terms together. And the problem here is that I have a 2. So I need to factor out that 2. And so if I factor it out, I'm going to have 2 divided by 2 is x squared. 8 divided by 2 is 4. And if I check, I get 2 times x squared is 2x squared. 2 times 4x is 8x. So our next step is take half of b. In this case, b is 4, so half of b is going to be 4 divided by 2 is 2. And then we want to square it, so 2 squared is going to be 4. So now we're going to add and subtract 4 minus 4. Okay. So if we have, so just really quick, just an announcement. If you are taking Math 1324, make sure that you click the link to go to the other class, because what I'm covering here is going to be for Math 1314. Okay, so now that we have our 4 and -4 here, we want to take out this -4. And so when I factor it out, then I have to be careful because there's a number in front of the parentheses. So we need to multiply this number 2 times the -4, which is going to be -8. And so if we go from there, now we have -8 plus 7 is -1. And the x squared plus 4x plus 4 is going to factor as x plus 2 and x plus 2. So again, notice that when you took half of b, so take half of 4 was 2, and that's the numbers that we used here. So I can rewrite this as 2x plus 2 squared minus 1. My vertex is going to be -2 and -1. And our axis of symmetry is that first coordinates here, so that's going to be x equals -2. Okay, so now let's look. I think this will be the last one, but let's look at this one here. So again, we want to factor out the group together the x terms. I have a number in front of x squared, so I'm going to factor it out. So I end up with 5x squared, or 5 times x squared is 5x squared, and 5 times 3 is 15x. So now I want to take half of 3, and I'm going to do the work up here. So take half of 3 and square it. So half of 3 is 3 divided by 2, and if we square it, we get 9/4. So this 9/4, I'm going to add it and subtract it into the parentheses. Okay. So now we're going to take this 9/4, we're going to take it outside, but if I want to remove the 9/4, then I'm going to have to multiply it times the 5. So let me get my pen out really quick so I can just circle something really quick. So we're going to take this number out, but we have to multiply it times 5. And so that work, I went ahead and did it here. Okay, so -9/4 times 5 is going to be -45/4. And so I went ahead and put it here. Okay, so now inside of my parentheses, I have x squared plus 3x plus 9/4. And we know that this should factor out. But all of a sudden we have a fraction. And so that makes it a little bit harder to factor. But if you remember the shortcut that I've been mentioning, when you get your two factors, you're going to use whatever you got when you took half of that number. So if we had 3 and we took half of it, we ended up with 3 halves. So if we factor this, then we have x plus 3 halves times x plus 3 halves. And so that's where the shortcut is going to help us. So now I can rewrite this as, well, before I do that, if I want to add negative 5 minus 45 fourths, I need a common denominator. So this 5 I can rewrite as 20 divided by 4. And now these are the same, so I can go ahead and combine the numerators. So negative 20 minus 45 is negative 65. And then I can rewrite my equation as 5 times x plus 3 halves squared minus 65 fourths. So my vertex is negative 3 halves and negative 65 fourths. And my axis of symmetry is negative 3 halves. Any questions? Okay. So here we have, now just kind of continuing on, we have write the standard form of the quadratic function whose graph is the parabola shown. So they give you this parabola and you want to write the standard form. Since they mentioned the word standard form, then I encourage you to write what that is so we can see it. And from the standard form, we know that your vertex is HK. So in order to write the equation, you're going to need to have the vertex and at least one other point. Okay. So if we look at our graph, the vertex is -1 and -1. So that's right there. And then you want to pick at least one other point. So you can pick any point you want, but just make sure that whatever point you pick, you know the actual coordinates. So I'm going to go ahead and pick them 0, 0. So once you have these, we can plug it into the standard form. So I have f of x. Remember, f of x is y. So in my point, y is 0. And then I have a, and then I have x. X is 0 in the point that is given, minus h. H is -1. And then k is -1. So we simplify, we get negative negative is positive 1. And then if we square it, we get a 1. And so we're going to add the 1 to the right side. So we end up with 1 equals a times 1. Divide by, or a times 1 is just a. And so now a is equal to 1. So they didn't ask us to solve for a. So we want to make sure we go back and write the standard form. So f of x is equal to a. A is 1. And then I have x minus h. H is -1. And then we have our k. So negative negative is positive, and you don't need to write the 1 again. Okay. So my standard form would be this equation. So let's do this one. Here they don't give me the graph, but they give me the necessary things, right? I have a vertex and I have a point. And so I'm going to start by writing the standard form. That way I can have it in front of me. And then the vertex here, that's your h and that's your k. And then your point, that's your x and y. So we're going to substitute those values. So y is 3 is equal to a, x is 0, minus h, which is -3, squared, minus 15. So if we simplify, we get negative negative is positive 3, and 0 plus 3 is 3. So if we square it, 3 squared is 9. So I'm going to add 15 on both sides. So 15 plus 3 is 18. And then if we divide by 9, then we get 2. A is equal to 2. So if we plug that in, then we have a is 2, h is -3, and then we have our k. So if we simplify, we're going to end up with 2 times x plus 3 squared minus 15. Okay. So now what we want to do is, a lot of what we do in chapter 2 is going to be finding these x-intercepts. So the x-intercepts are the points where the graph crosses the x-axis, and your instructors might be using different names for them. And so I went ahead and put the 4 names that we have here. So they're called x-intercepts. In chapter 2, the word we use the most is zeros. and then we have roots, or we say solutions. Okay, but either way, to solve for these x-intercepts, they have something that is special, and that is that y is always going to be 0. And so we use that idea to help us find the solutions. So there's different ways to find those zeros. You can use the square root property, but it's not always going to be applicable. You can't use it all the time. Factoring is a good strategy too, but you can't always use it. And then we have the quadratic formula. The quadratic formula, you can use it always. Okay. And so sometimes, oops, let me go back. So sometimes the parabola or the quadratic function might not have x-intercepts. If it doesn't have x-intercepts, it means that the graph is somewhere up here, or the graph might be somewhere down here, and so it's going to cause it to not have x-intercepts. And then sometimes it might have one x-intercept, right? Or it could have two. So in this case, it has 2. Okay, so just know that the quadratic functions can have 2, 1, or 0 x-intercepts. So let's look at a couple of examples for the square root property. So example 1, first thing you want to do is set y equal to 0. And in order to use the square root property, whatever's being squared has to be isolated. So we're going to add 4 on both sides, and we get 4 equals x squared. Take the square root on both sides, and so we get x is equal to plus or minus 2. So these are going to be your zeros. On example 2, we're going to let y equal 0, and the thing that is being squared is going to be this part. So that has to be isolated. So first, I'm going to add 27 on both sides. So I get 27 equals 3 times x minus 4 squared. Then I'm going to divide by 3. So I get 9 equals x minus 4 squared. I can take the square root on both sides. And so I end up with square root of 9, which is plus or minus 3. And then the square root and the square become 1, so we get x minus 4. I'm going to add 4 on both sides since I'm solving for x. And so here we get two answers. We have 4 plus 3, which is 7, and 4 minus 3, which is 1. So those are two solutions. And so if you notice in the graph, we have our two solutions here. Now, factoring, there's a whole session on factoring. If you missed that session, you can always find it in the YouTube channel that we have, and you'll be seeing those links coming through. And so if you struggle with factoring, I encourage you to watch that video. But factoring is one way to solve these equations, but it doesn't always work. So I also encourage you to try it, but if you're not able to get it, then we can go to a different strategy. Okay, so here this is going to factor as x minus 3 and x plus 2. And so if we set it equal to 0, then we have x minus 3 equal to 0 and x plus 2 is equal to 0. So our answer is x equals 3 and x equals negative 2. The last one is the quadratic formula. So this is your quadratic formula here. You can always use it. A is going to be the number that is in front of x squared. So in your general form, this is the general form, ax squared plus bx plus c. And so a is always going to be the number in front of x squared, b is always the number in front of x, and then c is going to be your constant. So if we look at our example, in front of x squared, I have a 1. In front of x, I have a negative 2. And then our constant is going to be negative 8. So if we plug that information, then we have negative b, which is negative 2, plus or minus b squared, which is negative 2 squared, minus 4 times a is 1, and then we have negative 8 divided by 2 times 1. And so if we simplify, we get negative is positive 2, negative 2 squared is 4, and then negative 4 times 1 times negative 8 is positive 32. 4 plus 32 is 36. And the square root of 36 is 6. So here we're going to end up with two answers. 2 divided by 2 is 1. 6 divided by 2 is 3. So my answers are going to be x is equal to 1 plus 3, which is 4, and x is equal to 1 minus 3, which is negative 2. Okay, and so these are all the different ways that you can solve for quadratic functions. The next section is going to be section 2.2, which is going to talk about polynomials. And I'm going to let Mr. Carizales take over for section 2.2.
Thank you so much, Ms. Chuka. Awesome. All right, guys, so let's go ahead and get started with section 2.2. Okay, so so a graph of a polynomial. Well, what is a polynomial? Okay, so if you guys remember back in the old days, the way they told you that a graph is represented with a polynomial is if you can draw this graph with a smooth curve. You never lifted up your pencil. The graph didn't have any breaks. The graph didn't have any sharp turns, right? So if you saw a graph that was continuous, right? That means that you were dealing with a polynomial. So, for example, the graph on the right is not a polynomial because there's a break. Even though it is moving forward, right? There's a break here where it stops here, and then this value doesn't exist here, and then it keeps on going. Okay, so again, graphs of polynomials are graphs that have smooth curves, no sharp turns, and again, no breaks like that. This example on the part B. Okay. Now, what I also like to tell my students is like polynomial. What does that mean? Well, if we break down to what polynomial means it's made out of two words: poly meaning many, and nomial meaning number. So many numbers, or you can think of it as many terms. So what this is going to referred to is that we're going to be looking at um, graphs that have many turns, right? And with these many turns, we may have more than multiple x-intercepts or solutions, just as Ms. Chuka had mentioned. And that's what we're going to review in this section. We want to find the solution for some of these polynomials. And again, what we're doing is going to solve for those x-intercepts. Okay. So again, another example to determine if the graph that we're looking at is a polynomial or not. If we look at the first graph on the left, the graph, again, they're all smooth curves. They're twisting and turning. That's fine. But there are no breaks. And if I look at the example on the right graph, we have a sharp turn. So since this is a sharp turn, this is not considered a polynomial. Okay. All right. So we are going to graph polynomials. And one of the things that we need to know in order to understand the behavior of the polynomial, to understand how the graph is behaving, we are going to perform something that's called the leading coefficient test. But in order for us to understand the leading coefficient test, we need to know if the function or polynomial that they're giving us is even or odd. Okay, so let me do a little quick review as far as functions or polynomials that are even or odd. And what I tell my students is this. The first thing that we need to do is, and just to review polynomials, the highest exponent that a function or polynomial have, that highest exponent is called the degree of the polynomial. Okay, so again, the highest exponent number is the degree of the polynomial. Now, if that exponent is an even number, then the polynomial is an even function or an even polynomial. If that highest exponent, the degree of the polynomial, is an odd number, then my polynomial or function is an odd function or odd polynomial. Okay, so if you look at here, The first graph here, we recognize this already, hopefully. We see that this is our parent function for the quadratic. So the degree of this polynomial is 2. So hence, this polynomial here is an even function. Yes? Same thing with the second example. Okay, I have f of x is equal to negative x squared. Since 2 is an even number, then I'm dealing with an even function. Now, here's where the leading coefficient test comes into play. If I am dealing with an even function, okay, and the leading coefficient, and let me review what the leading coefficient is, okay? So when I'm dealing with the degree of the polynomial, the leading coefficient is the number associated in front of the x, okay? So the number in front of the x of the leading um, coefficient, which is the one with the highest degree, that is the leading coefficient. So in this case, in this first example, in this first graph, that leading coefficient is a value of 1, but it's a positive 1. So if I have an even function with a leading coefficient of a positive number, my graph is going to point upwards, both to the left and on the right. It's going to point up. Yes? Let me see. So here is what I have. If my degree here is 2, then it's even. My leading coefficient is 1, is a positive. So the end behavior, the way the book says, or the way you might answer it on your homework, is that this graph is going to rise on the right and rise on the left. Okay. Now, if we look at this second graph, again, we know that the second graph is an even function, but my leading coefficient now is a negative 1. So whenever your leading coefficient of an even function is a negative value, okay, the end behavior is going to be like this. It's going to fall on the right and fall on the left, okay? So this is what's called the leading coefficient test. Now let's look at the next two graphs. If I look at the third graph here, we have f of x is equal to x to the third power, or we know from our library of functions that this is our cubic function, right? So the degree of this function, or the highest exponent that this function is going to have, is 3, right? So 3 is an odd number. So hence, this is an odd polynomial or an odd function. Now, what is the leading coefficient on this one? Or my leading coefficient here is a positive 1. So what that means is when I have an odd function and my leading coefficient is a positive value, the end behavior is this, and you can see it on the graph. It's gonna rise on the right and fall on the left. And what I like to tell the students, especially with the odd functions, is remember, we read graphs from left to right. So if it's if it's an odd polynomial, but the leading coefficient is positive, my graph is going to continuously going up. If you see, it's just, there might be a little twist and turn, but it keeps on going up. Okay. Now, oppositely, on this last graph, again, we're dealing with an odd function or odd polynomial because my degree is 3. Here, my leading coefficient is negative 1. So the end behavior based on my leading coefficient test for an odd function, it says it's going to rise on the left and fall on the right. Okay. So again, if I'm reading my graph from left to right, you see that it just continues going down. Yes. So this is what's called the leading coefficient test for polynomials. And knowing this information will allow us to graph um, these polynomials. So let's go ahead and look at some examples. Okay, so describe the left hand and right hand behavior of the graph of either of these functions. So let's look at the first one, A. So f of x is equal to 3x to the 8th plus 7x squared minus 2x to the 5th plus 4x plus 100. Now you're going to encounter this. Sometimes they're going to try to trick you. They're going to give you a polynomial which is not in general form or standard form, and they have all the terms, all the different terms not in the right order or in descending order. So what we need to look for is we need to look at the highest exponent. And if we see here, the highest exponent on this polynomial or this function is a value of 8. So 8 is the degree of my polynomial. So because this number 8 is an even number, then a is an even function. So now let's look at the leading coefficient of this polynomial. The leading coefficient here is a 3. This is a positive number. So because this is an even function and my leading coefficient is a positive value, the behavior or the end behavior of this graph is going to rise on the left and rise on the right. Yes. So again, I brought up my little template here. Again, which a falls under this first graph, right? It's an even function. My leading coefficient is positive, so it's going to rise on the left and rise on the right. So my answer is this one here. Yes. All right. So let's look at B. Have B here is an odd function because the highest exponent is 3. So then the degree of this polynomial is 3. So now look at my leading coefficient. Oh, my leading coefficient here is a negative value. So then I go into my um, template here for an odd function with a leading coefficient of a negative number. The end behavior is going to rise on the left and fall on the right. Yes? Okay, now let's look at the last one. So we have negative 2 times x cubed plus 9x squared plus 8. Now we got to be careful on oh, sorry, we're doing C, excuse me. Want to get ahead of myself. So let's look at C. So C here, we have a 6, 5, 8. See, this guy's on my way. Let me see if I go back. It goes away. No, it's not going away. Okay, so here we have a 6, 5, 8. And I believe that's just my constant. Okay, so what I see on this one, again, my highest exponent here is the 8. So 8 is an even number. So the leading coefficient for this one is the negative 4. So again, when I have an even function and my leading coefficient is a negative, the end behavior is going to fall on the right and fall on the left. Yes? So again, my degree is 8. It's an even function. So my leading coefficient is a negative number. So it's going to fall on the left and fall on the right. Okay? Now let's go ahead and look at the last one. Now on the last one, we got to be careful because they factor out at 2. So this 2, when I multiplied, is not going to affect my degrees. It's not going to affect my variable x because I'm not adding any more to these x's. So just be careful. If there was a x out here, it will change the degree. So you got to make sure that we multiply that back in order to find the true degree of the polynomial. But again, in this case, all they did was factor out a number. So my degrees or my exponents are not going to be affected. So I look, what's my highest exponent here? My highest exponent is a 3. So that means that 3 is an odd number, so I have an odd function. Now, where I do have to think about this factoring of the negative 2 is that if I would give it back to this, my leading coefficient for this one would be a negative number. It's not a positive, even though it's a positive 1 right now, but I had a negative 2 factored out on this. So again, on this one, I have an odd function, but my leading coefficient is still a negative number. So since it's an odd function with a negative number, the end behavior, again, falls on this one. It's going to rise on the left and fall on the right. And that's how you're going to ask these questions on your homework. And again, this end behavior is a great tool that will help us graph. And again, hopefully you see that we won't need a graphing tool if we know this one of these features, right, which is the end behavior of a graph. Okay, all right, so let's put it together. Okay, so if I observe the following graphs, okay, what we want to do is we want to go over when it crosses the x-axis. And again, as we covered already in 2.1, what Ms. Chuka said is whenever time when we cross the x-axis, we have the x-intercepts. And again, another name for the x-intercepts are our zeros of our graph or our solutions of our graph, right? So that's the reason why we mentioned that, because now it's going to be important for us to know this, right? So if we look here at this first graph, okay, this graph, the x-intercepts are labeled for you. we have an x-intercept at -1, at 2, and at 4. And if you see the polynomial basically was factored out for you to be able to discover these x-intercepts. You see here, what value for x would I put here for 2 that would give me a 0? Well, then that would be, sorry, a 2, right? So for this next one, I'm giving the answer. What value for x would I give here that would make this 0? And again, when I multiply by 0, everything becomes 0. Well, that's easy. If I put a -1 here, -1 plus 1 will give me the 0. And same thing with this last one. What value for x I can put here that would make this 0, that would make all of this 0? It would be a positive 4. If I put a x for 4, 4 minus 4 is 0. And again, it doesn't matter what these values would be. The fact that one of them is 0, 0 times anything will always give me 0. So one of the ways that you can graph is if you factor out your polynomial. And again, if I were to multiply all these terms back again, if I count the x's, I have 1, 2, 3, I would have a cubic function, right? That would have 3 x-intercepts, right? All right, so if we look at the second one, again, we had mentioned that touching the x-axis is also considered a 0. But one of the things that you need to know, and if you remember from the evaluating of functions, is whenever the graph is increasing and then it changes and then becomes decreasing, right? We call this, when it touches the x-axis, we call this a double zero. Again, like our quadratic, right? We can say that it has only one intercept at 0, but that 0 is counts twice, right? So we like to call this 0 a multiplicity. So you will have some homework answers or problems that they're going to ask you, what's the multiplicity of these zeros? And what that means is, in as an example, this one, the multiplicity of the 0 at -2 is 2. This counts for 2. When a graph touches and turns around, that 0 is counted twice, okay? So again, if you see here, I have a cubic function, and it makes sense that I would have 3 zeros, and you see the solutions here. The solutions for the zeros are x equals -2, at x equals 2, and at x equals -2 again. So again, this one counts twice, all right? So then let's look at this last graph, okay, this W-looking graph. If I see here, the degree of this polynomial is a degree 4. So at most, I'm going to have 4 solutions, or 4 x-intercepts, or again, 4 zeros. So here, we can see, based on the graph, I have a 0 at -2. Again, this 0 counts twice. It's a double 0, multiplicity of 2. And then we have another 0 at 2, 0. Okay, so again, the solutions for this graph would be 0, 2, -2, and 0. And again, we can find these by finding the x-intercepts of the graph. Okay, now this is what I was mentioning to you. So the multiplicity of zeros will determine the graph, well, if it crosses the x-axis or if it just touches it and turns around. Okay, so for instance, going back to my quadratic, okay, my quadratic is one of those where its vertex is at 0, 0, but it touched a 0 and then it changed directions. Yes, so that here, my 0 counts as twice, right? So it has a double multiplicity. Okay, so we can have what's called an odd multiplicity when we look at our cubic parent function, right? If we have our cubic function here, we have this graph where it's like touches it, right? There's a small curve that we don't see, and it gets more defined as we change values of our cube. Okay, so again, we can have what's called an odd multiplicity. All right, so let's put all of this together. Okay, so find all the zeros and determine the multiplicity of each of the zeros. So here we have f of x is equal to x squared minus 2x plus 1. Okay, so first, what we need to do is let's solve for the x-intercepts. And again, we can factor it, we can use our square root property, or we can use the one that always will help us is the quadratic. But again, let's try to always use the easiest method first. And I like to always try factoring. Factoring, I think it's the easiest thing to use, and and the quickest, right? So again, well, what I want to do is if I want to find the zeros for this polynomial or this function, I set y equals to 0, right? F of x is replacing the variable y, so we have 0 is equal to x squared minus 2x plus 1. So what I'm going to do is I'm going to factor this, okay? Again, I want to find two numbers. When I multiply them together, give me a positive 1, and when I add them together, give me a negative 2. So this factors out with a -1, right? A -1 times a -1 gives me a +1, and -1 plus -1 gives me a -2. Again, um, so this factors in to x minus 1 times x minus 1. Again, we can use our property of 0, that when we're multiplying two numbers, the only way that we can get 0 is if this is 0 or this is 0. Again, we can separate it if you don't see it. 0 is equal to x minus 1, and 0 is equal to x minus 1. So that means that the value that will give us 0 here is 1, right? These both the same. But this is telling me that because I have two of this means that my graph is touching at this point and turning around. So this graph, this one has a multiplicity of 2, yes? So again, you can see clearly on the graph. This graph got shifted 1 unit to the right compared to my parent function, and my vertex now is at 1, 0. But it touched and then turned away, okay? So again, this is how I can find my solutions. Right? Let's look at this. Find the real zeros and determine the multiplicity of each zero. So we have t to the fourth minus t cubed minus 30t squared. Again, what I'm going to do is I'm going to use a quadratic method to solve for this. So the first thing that I see is I'm going to set it equal to 0, but I see that in this polynomial, they all share a t. So I'm going to factor out the the smallest t that I have. And the smallest t that I have is a t squared. So I'm going to factor that out. And when I do that, I have t squared is equal to t squared minus t minus 30, which is awesome. Now it helped me even simplify. Um, so this first one, if I break it up in pieces here, the t squared, okay, I know that I'm going to have a double zero here. But here, let me factor this guy out. Two numbers, when I multiply them together, give me negative 30. And when I add them together, give me a negative 1. And what are those two numbers? 6 and 5, right? A negative 6 and a positive 5. A negative 6 times a gives me a negative 30. And minus 6 plus 5 gives me a negative 1. Okay, so this factored out to t minus 6, t plus 5. Again, um, I'm going to use my 0 property that says when I'm multiplying numbers, the only way that my answer is going to be 0 is if either t squared is 0, or t minus 6 is 0, or t plus 5 is 0. Yes? So again, hopefully you see here, take the square root of both sides. Again, this is a double 0. Um, Here, what value would I put here for t that would give me 0? Well, if t is 6, 6 minus 6 will give me 0. And what value for t can I put here that would give me 0? Well, if t is negative 5. Negative 5 plus 5 is 0. So if we look at here, we have at t equals 0, we have a multiplicity of 2 because it counts twice, okay? And the t equals 6 and the t equals negative 5, we have an odd multiplicity because it only happens once, right? And the multiplicity for those would just be labeled as 1, right? All right, so we can take this information and then we can graph it, right? We can first start with labeling where these zeros occurred. I had a 0 occurred at x equals negative 5. Have a double 0 at 0, so that means that the graph cross touched and turned around. And then I have a 0 at 6, sorry, at 6, positive 6. So it's right here, right? And then again, I could have used my end behavior to know the behavior of this graph or how to graph it. Again, this is the degree 4 polynomial, so that means that it's even polynomial. The leading coefficient is a positive value, so that means that my graph had to be pointing up on the left and pointing up on the right. So again, you can barely see it on this graph, but again, it's pointing up here. It would have come down, cross at this x-intercept, which would have been a -5. It does a turn down here. It comes up, touches at 0, turns around, and then curves again, and then crosses at 6 and goes up. Again, if we can put all this together, this will help us graph. And again, it's easy to answer those graph questions on WebSRM because it's always multiple choice. So if you understand the behavior and you know how to find the zeros, picking the right graph is always easy, I hope. Okay, so let's look at this example. Let's sketch the graph. Let's actually sketch it. Now they're not asking to solve anything. They are asking us to sketch it. Okay, so the first thing that I see is I want to find what type of polynomial is this. So the degree of this polynomial is at 3. That means 3 is an odd number since this is an odd function. What is the leading coefficient of this polynomial? Well, the leading coefficient of this polynomial is a positive number. It's a positive 1. So the end behavior of this polynomial, since it's an odd function and with a leading coefficient of a positive number, this graph is going to rise on the right, fall on the left. Okay, so I know that. So in order to sketch again, I did a little table to go through these to help us graph. So again, I identified the end behavior. Okay, so now let's find the zeros. So to find the zeros, I first set the polynomial or the function equal to 0. Again, then I saw that both terms were sharing an x. So I'm gonna factor by the greatest common factor. The smallest one is the one with the highest exponent, which is the x squared. I factor that out. This gives me x minus 3. Again, set them equal to 0 to find the zeros, the true zeros. So 0 is equal to x squared, 0 is equal to x minus 3. So again, on this one, I know that I have a multiplicity of 2 because of the square root. The 0 counts twice. It's an even multiplicity. This 3 only happens once, so it's an odd multiplicity. So I only have one x-intercept. Give me one. Sorry. Okay. So I have my zeros. Okay. Now let's find the rest of these. We can find the y-intercept. The y-intercept hopefully is easy to solve, right? If I want to find the y-intercept, I set x equal to 0. And if I put 0 here on my polynomial, 0 cubed minus 0 squared is going to give me 0. So my y-intercept is at 0, 0. So let's go ahead and graph, okay? So the first thing that I'm going to do is I'm going to plot my zeros. So I have a double multiplicity at 0. I have a 0 at 3, okay? And I know my end behavior because I know this is my leading coefficient was positive. It's going to fall on the left and rise on the right. So I will put that. Again, this is all I know. I know that it's going to fall on the left, and that's accurate. I know it's going to rise on the right, okay? And I know that's the end behavior. That's what the graph looks like. But if you see here, we have this middle part that we don't really know what's going on. Now, I know that it had a y-intercept at 0, so that's already covered with one of the zeros that I had before, but it also tells me that the 0 had a double multiplicity. So I know that to the right of the 0 here at the origin, I know it's going to turn down, okay? So what I really want to know is I want to get a point that's between 0 and 3 to tell me what the behavior of this graph is happening right in the middle here. So that's what I'll do. I'm going to do an additional point, and again, I want to be smart about it. I want to pick values that are between the 2 points that I really want to know. So the 2 points that I picked were the 2 points that are between 1 and 3, which is 1 and 2. So when I plug it, when x is 1, I get a value of -2 for y. When x is 2, I get a value of -4 for y. And again, I just picked another one just to be a little bit more accurate. I picked 2.5 for x, and my y value was a negative 3.125. And if I plug those points in, I can go ahead and plot them and try to do my little smooth curve. Yes? So again, knowing the end behavior of our graphs, finding the zeros of our solution, we don't really need a graphing tool to graph these polynomials. Okay, so again, just to make it nicer, this is what you would see on WebAssembly, right? WebAssembly would be this is the selection that we use to select your answer. Okay. So again, I hope that our session helps you. We love that you are joining us every Friday for these review sessions. Good luck with your classes and hope to see you again next Friday. I'll pass it now to our presenters. Thank you so much for joining us.
Thank you so much to Mr. Carrizales and Ms. Chuca for their presentation today. Please join us next week so that we can review for the math. We can review for the Math 1314 and Math 1324 next week. We will be reviewing for the Happy Math Hour, Math 1314 is synthetic division and complex numbers. Math 1324 is solving exponential and logarithmic equations. And for the student success presentation at 1 p.m., we have the El Paso Children's Garden presenting. Okay, so thank you very much, everyone, for joining us today. You all have a great weekend, and don't forget to fill out the survey and also use your Tejano virtual events code. Thank you very much.